Rightio. Welcome everybody, and it's lovely to be here. I don't know why it always does that to me. It always flicks to the second slide. So this is a combination of my honours work, which I did in conjunction with Lithodat under an arc linkage project, and I was very fortunate to have a whole heap of collaborators down here in the bottom right, and so hopefully this is some really interesting stuff that you guys enjoy. So the motivation here was to develop some numerical techniques to really target deposits, particularly deposits that are buried below the surface. We used Papua New Guinea and Indonesia, that main island, as our case study here, and we talk about porphyry copper deposits, but the goal is for the workflow to be transferable to other regions, and you could also apply it to different mineral systems as long as you have constraints on the emplacement depths. So why look for copper or any metal? This is not something unfamiliar to most of you, but we know copper is an important material for electronics, and so we need a huge amount for our transition to net zero. We've been spending a lot on exploration, but the trends are not looking so good with some of this exploration. The yields we're finding are decreasing, the ore grades that we're finding are also decreasing, and the better discoveries we're making are those at depth. So they're all pointing to the general idea that our large surface-based deposits have more or less been found or have been mined, and therefore our traditional exploration methods, which tend to focus on surface expression, are becoming less effective. So we need to develop new methods to effectively find new subsurface deposits. So one way in which we've been advancing our techniques is through machine learning. So what machine learning, the type of machine learning workflow that I built on in my project was using the known deposits and their locations and their ages, and then we combine those with kinematic data from tectonic plate reconstructions, so that the algorithm can find patterns and then predict through space and time where we have deposits formed. So some of that kinematic data looks like the distance from the subduction zone or the nature of the subducting slab, things like the obliquity and the dip angle and the rate that it's going down. So this model here, I'll just play it again, is the model that I will be building on by one of my co-authors, Hassan. So what these focus on are the mineralization component, and that's fantastic. We have predictions for when and where deposits are being in place through deep time. But what is lacking is any information about what happens after we in place this deposit, and this is an extremely important process.
Sorry, Addison, can you share your screen?
Oh. Sorry for those on Zoom. Flying blind.
Yeah, that's better.
Okay. Well, for those on Zoom, these are the mineralization predictions based on machine learning. So they predict through space and time where deposits are. The X's are the locations of known deposits. I'll play that one more time so people know what we're talking about. All right. So what they do is we're focusing on the mineralization part. What we're lacking is information about what happens afterwards. And what happens afterwards is really important because these deposits typically form 2 kilometers or so, maybe 3 kilometers. Sometimes they even form at 7-kilometer depths. So we need some processes to occur after their formation to bring them towards the surface so that we can discover them and mine them. So the bulk of our work focused on developing these preservation predictions. So then we combine these with the mineralization or formation predictions to get a complete set of numerical outputs. All right, so the preservation predictions, the way we developed those was through landscape evolution modeling. So the general gist of how this model works is we have an active margin, so a subduction zone setting, and that is causing intense uplift, forming our mountain belts. Associated with the downgoing slab is the release of fluids and our volcanism, which is associated with the formation of these porphyry deposits. As we erode the top layers, of the mountain belts, these deposits move closer and closer to the surface, or the older deposits move closer to the surface. And the way in which we are taking off material from the top is through erosion and surface processes. So that's shown up here, and they're driven by things like climate and sea level. So here is the general equation on the right of how the model works. I'll go through it a little bit more. So basically for each cell in your model, you have an elevation change over time, depending on your sediment flux and your vertical change. So the sediment flux are these surface processes that I talked about. So they include a fluvial model. So that's a stream power law model, which basically moves sediment from higher terrain down slope. And it's dependent on things like slope, erodibility, and the catchment area. And then we also have marine transport, which moves things down slope in the marine area. There's more detail that I can go on about these things, but I figured that's not what we are most interested in. So I'll just summarize, like these processes are affected by other things like paleoclimate and evolving sea level, which we included in our model. So they're forcing boundary conditions. And we also have diffusion as well down slope to give us some more control on how the morphology evolves. The vertical change is captured by three things. So we have tectonic uplift, which we impose. So that varies over time and space. So it's more concentrated where we produce mountains and less concentrated in the basins. We have dynamic topography, which is associated with mantle convection. So that's a broad scale, low amplitude effect. So here it's broad dynamic subsidence, which is bringing pretty much everything down, but with a low amplitude of effect compared to that mountain uplift. And then we also have flexural isostasy using a coupled model within the Badlands landscape evolution model. That's called G-Flex. And what that does is basically when you have erosion, you induce a rebound effect or an uplift effect locally. So that's these blue arrows. And when you deposit sediments, you get a local subsidence effect. Okay. So that is the general gist of how the landscape evolution model works. Now the calibration side of it. So the two calibrating data sets that we used were the the eTopo on the right, and we also had some sediment isopacks for the Gulf of Papua. Here on the left is the preferred model. So you can see it's quite a realistic model as far as numerical models go at this day and age. Now the calibration relied on a design of experiments workflow using a software called DOEGen. So the reason why we had to employ this kind of workflow is because I just briefly went over the amount of processes we had. So that ends up blowing out the number of parameters. So we had over 22 parameters which we needed to explore. And if you think about all the possible combinations of those parameters, it grows exponentially the more parameters you add. So what we do to handle all these parameters is we iteratively introduce new parameters and then calibrate those. So I'll work through an example. So for example, we have in this stage, we want to add 3 new parameters and we have 3 different values for those parameters that we want to test. We feed that to DOEGen and then it optimizes how many models to generate in which to explore all the different combinations most efficiently. So here, 45 models is the optimal number of models to generate. We run all those models on HPC, and then we validate all the models against the independent data. So the sediment thickness and the topography data. From that, the software will tell us things about the parameter effect and which models are the best overall. So we do this workflow with each different set of parameters that we introduce. So we introduce a couple of parameters to the parameter space, refine those, and then we have to reiterate and refine all the previous parameters until we get a total refined parameter space. We do this a couple of times, adding parameters at each stage. So you start off with the initial estimates from previous stuff, and then you add in some different fluvial models and some associated parameters to introduce complexity, and then more complexity is added in each stage where you add more and more things. And then we end up with the preferred model. So in this, through this method, we calibrated 22 parameters, and that took around over 2,400 models to do this. So there's a huge amount of models, and a large number of processes. So, for example, a lot of the previous work on landscape evolution models, they've calibrated 1 to 5 parameters. So, the jump to 22 is quite significant, and that's really been enabled by that DOE-Gen software. All right. So now we have our preferred model. So I'll run through some of the key events of the evolution from our model. All right. So a few things. So Uplift in this model was purely vertical. So we have terrain accretion events throughout the history. So we had to impose vertical uplift so they effectively raise from below sea level. So for the purposes of this presentation, I've just drawn little blobs to somewhat represent where those terrains would be, and then you'll see them crop up once they collide and produce uplift. So we start off at 15 MA. This is based on some paleogeographical studies for the initial topography. And this is why we start at 15 MA, because this is the latest stage of orogenesis, and this is all the deposits that we've discovered on the margin are younger than this age. So we have the Marimuni arc, which is this thin stretch, and this is uplifting from the model start time, 15 MA. And then we have the Halmahera arc at the top here, which is approaching as the Proto-Solomon Sea subducts underneath. Right, and then at 12 MA, we start uplifting the Papuan Peninsula based on some Marimuni arc volcanic ages for this area. And we explored a couple of different timing uplift onset timings, and 12 MA seemed to fit the best. Then between 8 and 6 million years ago, we have the docking of part of the Halmahera arc, which forms the Boani-Torricelli ranges, and that chokes the subduction zone, so that changes to oblique convergence, and we have a polarity flip for the remainder of the subduction zone. This change in convergence causes the uplift in the central fold belts to spread southwards, so they get thicker in the north-south extent. Also at 6 MA, we have increased uplift in the Papuan Peninsula due to the reactivation of the Owen-Stanley fault zone. Okay. And then we have the reinitiation of subduction at 4 MA. So this arc here creates between around 4 to 3 MA, and that produces the Finisterre and the Adelbert terrains, or ranges, either or. And then we have continued subduction and continued uplift of the central fold belt and the peninsula, while the Boani-Torricelli ranges at the top, they stop uplifting around 3 MA due to the change in focus of deformation. Okay, so now I've got a little animation to show that. So we start off with Marimuni arc, and then we have the accretion of the northern terrains here, the Boani-Torricelli, and then we also have the accretion of the Finisterre. Can I get that to play again? There we go. So northern terrains start propping up here, and then the Adelbert and Finisterre on the right here laid on. And you can also see quite thin through the central fold belts, and then after about 6 MA, they spread southwards. So I'll quickly go through some of the results for uplift and erosion. So I spoke about flexural isostasy. So on the left here, we can see the net uplift and subsidence due to flexural unloading throughout the entire 15 million years. We can see that we've had, in some areas, over 6 kilometers of uplift due to flexural unloading, which is massive, and another piece of evidence to show that flexural unloading is important. It's not something that we should ignore. And then we have the tectonic uplift rates for 2 time steps up here, and we can see that the calibrated uplift rates are huge. This is the Boani-Torricelli ranges being uplifted here during the docking. So that's 1,000 meters per million year, and a little bit less so in the central fold belt. And then once we move to a younger, more recent time step, the central fault belt. The uplift is thicker, a wider range, and we get substantial uplift of 1,200 meters per million year. So these are massive uplift rates, and they do match some of the local field data. So if you're really interested, I can give you some details on that later on. Now, the erosion. So on the left here, we have the cumulative erosion over the 15 million year period and the deposition. So we can see the deposition is quite diffuse. It's really smooth. That's because we had a really high diffusivity for the marine deposition. So that's that hill slope diffusion. We've really pumped the diffusion on that. And the reason we did that was to really effectively move sediments into the basin so that we're not choking any of the sediment transport, because what we're really interested in is the sediment volumes in the Gulf of Papua. We weren't too worried about the sediment distribution because we're focusing on the mountains. We just want to constrain how much material was coming off the mountains. So now for the erosion, you can see the older parts of the Maramuni Arc or the fault belts, they have a massive amount of erosion as well. They have up to 14 kilometers of vertical unroofing, whereas the younger parts have more like, it's hard to see, but about 6 kilometers or so. The rates, you can see here, so the rates are also quite high. They're also around 1,600 meters for the younger time steps and more like 800 meters for the older time steps. So here, for example, we can see there's a lot higher erosion in the Irian Jaya. So that's arising from increased precipitation in this area, which is based on our paleoclimate model. And the increased erosion in general in the younger time step is due to higher slopes. There's more elevated terrain, so larger catchment areas and increased precipitation in general. Okay. So now I'll compare some of the model results to some external data to really see, to really check if what we've got is reasonable. So what we did was we backtracked the emplacement depth of some discovered deposits. So we know the locations of these deposits and we have radiometric ages for when they were mineralized. So we backtracked using the erosional history to figure out the emplacement depth. So where we get a range of depths, that's when there's a range of mineralization ages. Okay, so these are the colored pentagons and squares. And then we've compared that to some global data. And on the x-axis here, we have some geochemical trends. So what we can see is that the results from erosional unroofing alone really well capture the general trend of deepening emplacement when we get more copper over gold, and deepening emplacement when we have less gold concentration. The cluster is also, you can see a pretty good overlap between the cluster of data. Now, there is some systematic biases that you might observe. So the predictions from stratigraphic relationships, so these are the gray circles, tend to have the shallowest emplacement depths, while our predictions from using fluid inclusion methods have slightly deeper emplacement. And then the model results seem to have deeper emplacement again, particularly when we look at the gold concentration plot. So these might point to the model slightly over predicting erosion, and that's definitely possible. But really the broad scale trends have been really well captured. Now, there also are some outliers. So for example, this pink square here is Friday River. So this deposit is 12 million years old. And some authors have previously commented on this. They've investigated using thermochronology studies. So that's Hill and Hall. And they noted that this deposit would not have survived the Miocene denudation because it is so old. So they hypothesized that thrust sheets or some sort of mechanism where it is buried post-emplacement by fault movement has preserved that deposit. So it's moved it down so that the erosion has not destroyed the deposit. So you could say that might play some component, probably does play some component for a lot of these deposits, because porphyry deposits do tend to form along fault zones. But so we have some outliers there. And that is a really good explanation for why we have might have some of these outliers. but we've achieved our motivation quite well. Can we use erosional unroofing and not consider fault movement to capture the data, to a broad extent? And the answer is yes. Okay. And then what we did was we compared the unroofing histories to some thermal models. So these envelopes are statistically valid thermal models developed from thermochronometers like appetite, fish, and track. And the solid lines are the exhumation paths from the model. So these are from the same location as where the thermal models were, the thermal model samples were collected. So then we equated temperature and age to depth age using this geothermal gradient here. And I need to stress that using these kind of linear geothermal gradients are, very, they're approximations. So they're not always linear, they don't hold beyond 5 kilometers, and they often change spatially and temporally. So it's really, this kind of comparison is really just to see, do we get the timing right and do we get the general gist of things? I'm not terribly concerned if the amplitude doesn't necessarily overlap. If we had good constraints on the actual geothermal gradient, then we could really scrutinize it a lot more rigorously. But what we see is a pretty good agreement between 0 MA and 7 MA. They seem to follow relatively well for most plots. This one seems to be a little bit, the erosion seems to be over-predicted for this plot here. So that's good. What's going on between 15 MA and 7 MA? So here we're focusing on the Papuan fold belt, particularly just down the left there in the greater Juha area. So in this area, or across most of New Guinea, we have the deposition of the Darai limestone between 15 and 7 MA. So you would expect some deposition or some growth, deposition of the strata because we're depositing limestone on top. So that's what's seen in the thermal models. We didn't model carbonate platforms in the landscape evolution model, so we don't expect to capture that. So that's okay. Now, what makes this more okay, for lack of a better term, is all the deposits in the Papuan fold belt are younger than 7 million years. So we're not too concerned if we're lacking some carbonate deposition because we're not worried about the unroofing of deposits older than 7 MA because they don't exist. There's no subduction zone there. So do we capture the erosional history when it's relevant? Yes, we do for this area in particular. Okay. So now that we have a pretty good, now that we're relatively confident in the model results, they can reproduce what we're looking for based on our motivation, and that is to see if we can use erosional unroofing to capture the broad scale trends. Now we can go on to make our predictions about preservation. So here we simplify emplacement, where we assume it occurs between 2 and 3.25 kilometers. Now this is the depth that most of the largest deposits around the world have been emplaced. And then we also define near surface as being within 500 meters of the surface. So using these constraints for every cell, we get the exhumation path, which looks like this, and we figure out what mineralization ages fit those constraints. So for this particular cell, we can see that the 2 MA, so the 1 MA is just outside, but if we have deposits forming at 2 million years and 3 million years ago, they would likely be preserved within 500 meters of the surface. Okay, so now I'll go through the same thing with a slightly different diagram just to make sure it's really clear. So what we have is from the machine learning predictions, basically a stack of probabilities of deposit formation. So 1 million years ago, 76% chance of a porphyry deposit being formed in this area. 2 million years ago, 68% chance, and so on and so on and so on. Then we go through and we do that exhumation path and find the constraints, and we figure out that the 3 million year and the 4 million year deposits would likely be within 500 meters of the surface. Anything older than 4 million years has been eroded. Anything younger than 3 million years is deeper than 500 meters. And then we use that to produce this map. So here we have two deposits that would be within 500 meters of the surface. So we just pick the highest probability and we display it here. So we can see that most of the central fold belt has some prospectivity, whereas the bird's tail, there's nothing within 500 meters. Everything's been eroded. I'm not sure if you can see it, but in this little strip here, we have both hashes. So that means that there's nothing within 500 meters. We have had deposits that have been eroded, and we have also deposits here that would be that the model predicts is situated below 500 meters. There is also we didn't plot any hatchings here as well in where we have probability. So there might also be deposits, or there are deposits that have been eroded in this area, and there are deposits that are deeper, but we just didn't put the hatching over because it's a bit too visually stimulating. Okay, so what do we see? We see really high prospectivity in the Bawani-Torricelli ranges, the Adelbert ranges, and in the Papuan Fold Belt. We see eroded deposits in the Papuan Peninsula when we know there are heaps of deposits here. It's a very prospective area. And we also have deposits preserved, but with a low probability of emplacement for the Irian-Jaya when we have the world-class Grasberg deposit in that area. So I'll go through and talk about the negatives first. Why do we have low prospectivity in the West? So we have the 3MA, Grasberg, and Erzberg deposits. What does the the preservation predictions say? They say any deposit formed around 3 million years ago is likely to be preserved. So the preservation predictions look good. So now we turn to the formation predictions. And we can see that there's very low probability for any time step around 3 million years. It's 0.4 and lower. Now, why is that? It's because there's actually the deposit's not in the data set. Oop. I've gone back a lot of slides there. There we go. The deposit is not actually in the data set. So you can see why the machine learning algorithm would say there's not a very low chance because there is no deposits in the West. Why isn't that deposit in the data set? It's because it's not in the global data set that Hassan used. I had to dig through to find a PhD thesis to find the geochronology, the emplacement ages for those deposits. Okay. So if we included the Grasberg deposit in the machine learning stuff, that would hopefully rectify some of those issues. Now, Papuan Peninsula, why is there no deposits at all? So, sorry, I'll go back. So these deposits here are between 4 MA and about 12 MA. However, the machine learning model predicts emplacement only at 15 MA. So why is that? Sorry. First, we have some missing subduction zones. So the tectonic model used here was a global tectonic model. If we look at some regional tectonic models like Savin's, which is also what I based my landscape evolution model off, we do have subduction zones along the Papuan Peninsula after 15 MA. And we have a lot of evidence for subduction zones there. We have Marumuni Arc volcanics in the Papuan Peninsula from 12 million years onwards. And we have lots of porphyry deposits. So improving the subduction zones in the plate reconstruction would help. And maybe some of these deposits are not directly subduction related. Maybe they're not typical 4-arc setting that we are attributing them to. Yeah. Now, looking at these terrains. So beforehand, I spoke about how these terrains were simplified to vertical uplift to model their accretion. So that means that they effectively rise from below the ocean. So we need to be careful when we make preservation predictions, because the erosional history is not reliable if it's underwater, right? So, for example, if we look at the Finisterre ranges, they're exposed above sea level at around 3 million years ago in the model. The age of the predicted near surface deposits, which is here, is 15 to 4 million years. So we should ignore those. The Adelbert, 2 million years, it was exposed above sea level 2 million years ago, and the age of the predicted deposits, 15 and 5 million years. Okay, so we should discount those terrains. They did not emerge above sea level until well after their emplacement predictions. The Guinea-Torricelli ranges, they were exposed above sea level around 7 million years ago, and by and large, most of the deposits there are that purple color, so they're 6 million years and younger. So those results are reliable there. Okay, I'm missing a good slide. There we go, go back. So what we can say is that the Guinea-Torricelli ranges and the Papuan Fold Belt really prospective. We can see that it's in good accordance with our known deposits, and we can see lots of small pockets of really high probability, which would be really helpful to potentially direct some more localized exploration efforts. So that's the point of this tool, really, is to be able to vector us towards finding new regions, new greenfield regions. Okay. So there's some improvements that we could make to this model. So first of all, if we were to change those vertical movements of the terrains to horizontal movements, that would rectify a lot of issues. So to do that, we'd need some constraints for the original geometry, or we'd have to guess. And we'd need some constraints for the deformation of those terrains, what the nature is. If we do have those constraints, particularly the deformation constraints, they're not widely available for New Guinea, but if they were to become available, there were studies done on those things, we could do that computationally using a program like Underworld, which can handle these horizontal movements and deformation processes, as well as and coupling that to landscape evolution. And I should also state, with the deformation processes, if we were to do this in Underworld, we could then include things like faulting and folding, as long as there was constraints, and that would also bolster the model as well. And then one big thing is the incorporation of glacial processes. So we know some of New Guinea is currently glaciated, and we know back through time that obviously New Guinea has been moving north with Australia, so it only gets colder as you move back in time, and we've just come out of an ice age, geologically speaking. So glacial surface processes would be really important as well to really fine-tune some of that morphology and erosion of the mountains. Okay, so here we developed a new approach to regional scale prospectivity. We combined mineralization and emplacement predictions, so those are the machine learning based predictions, and we combine those with some preservation predictions using landscape evolution models. So we combine those to make this map. I called it an IMAP. I used to like the name, now I don't like it very much, but it stands for Integrated Mineralization and Prospectivity Predictions. So importantly, the workflow is designed so that we can apply it to other regions, and hopefully we can adapt it to other mineral systems with constraints on the depth of emplacement. Thank you.
So any questions? You might want to just your mic around.
You got one online first.
Yeah. Okay. Do you want to? Yeah, I have to read. No mention of volcanism in the process model. Volcanism is a very important part of epithermal deposit formation, and also landscape evolution, e.g. explosive volcanism, can rapidly remove large volumes of material. Were any of these effects considered in the modeling? And if not, how could they incorporate in the future?
Yep. So the volcanism part is encompassed in the mineralization predictions. So they are using subduction zones, which are associated with magmatism and the development of these deposits. Specifically, we focus on porphyry deposits because we know the depth of emplacement. Epithermal deposits, they don't have a very good constraint. We don't have good constraints on the depth that they form because they form at a wide range of depths. Now, with the volcanic explosions to exhume deposits, we didn't make any attempt to include that in our model because the focus is really on erosion line roofing. Now, to do that, you'd need constraints through deep time as to where we've had volcanic explosions, and we'd need some numerical models to capture things like how the blast would actually affect the exhumation and the distance from the blast and things like that, and whether or not the blast would actually destroy the deposit. So it would be maybe possible, but very tedious to do. You would need to do it individually for each volcanic explosion. But yeah, so it was outside of what we were looking to do, really. Yeah, but I think, well, the results they look really good using erosion line roofing alone. So that really shows that we could move forwards focusing just on this for the meantime. And obviously the incorporation of more things like that would definitely improve results, but they wouldn't improve them, immensely. That'd be like a second order improvement. But at least that's what I would think.
We have another question online, but we'll go to the room first.
I think this was part of your. You mentioned this was part of your honours. Is the plan for your PhD to apply this to the rest of the Pacific, or what's the go moving forward with this?
So the plan is to apply it to Eastern Australia. So at the moment I'm developing some reconstructions and digitizing those into G plates, and then we'll develop some paleogeographic studies and eventually bring it back to the landscape evolution stuff. So I need to build a fair bit of digital infrastructure to allow this landscape evolution modeling, and I will be applying it to the east coast of Australia. Whether or not I probably won't focus on porphyry deposits, so I'll probably look at applying it to a different mineral system, but that's a little bit down the future.
So David Upton online is asking about could this be applied to the Tasmanites, for example, the Stavely are?
Yep.
Yeah.
Yep, that's the goal. But some of the issues, not the issues, but yeah, you need to make sure that where we apply it, you should probably have reasonable idea of the balance between the emplacement age and the erosion rates. If you place something too long ago and the erosion's too high, everything's going to be gone, and vice versa. If you place it too late and the erosion's low, it won't be in place. So the Stavely belt is quite old. I haven't looked at yet as to what the erosion rates are. So that's also why I won't necessarily be looking at porphyry deposits. We'll see what's most prospective there. So I can't speak too much about that right now, but it is applicable. We could give it a go.
And then another, someone says, thanks, Addison, is your honours complete? Have you published this?
Trying very hard to publish. So
manuscript revision number 45.
I sent Sabina a revision today. It's getting there.
Questions in the room? Yeah.
What other type of you apply this? You say you're not looking to you look at it porphyry. I'm sorry.
What other type of mineral systems are you looking to apply this approach to?
Haven't looked too deeply into that at the moment, but one thing we're actually interested in is not volcanic related, but like laterite deposits, because we have constraints on the erosion. We can predict some stuff about that. So volcanic related stuff I really haven't looked into outside of porphyry at the moment. So that is really something I've investigated in my last phase of my PhD as to what things we could apply this to. And another thing is, so a big issue sometimes is to do with the emplacement depth. So porphyry deposits are quite nice to have a generally regular emplacement depth. There's a lot of other deposits that don't. So if somehow these machine learning models or some other model were to also provide predictions for the depth of emplacement, then that would open up massively the other mineral systems that you could use or that you could search for.
We have one more question online. Maybe if you could open up the slide around the erosion, the total erosion.
Yep.
Nick was asking about, so I think in some places it shows 14 kilometers of erosion.
Yep.
Is that correct? And he's saying, well, that should mean that we should see deeply exposed metamorphic complexes in those areas. Is there evidence for that?
Yes, there's I can't remember what they're called, but Omar metamorphic. There are metamorphics, particularly in this area on the right, that are exposed. What are they called?
April
Ultramorphics and Owen metamorphics. Yes, so there are
lots of domes.
Yeah.
Oh,
I mean, it's like these are extreme numbers. I was skeptical, right?
Yeah.
But those were the numbers needed to actually get enough sediment volumes into the Gulf of
Yep.
Papua, which we know during this time is dominated by siliciclastic deposition, right? And you know, part of the Erie and Jaya story, why it's not so good, is that we didn't have enough data to calibrate that, you know, the western part, but the eastern part here, where we have the Gulf of Papua, you know, we worked with Oil Search Santos, and they had, you know, reasonably well constrained data, but it's extraordinary,
Yeah.
right? I'd love to hear what everyone else thinks. I mean, I guess you're in the humid belt, you know, you're at the
Yep.
equator,
Humid belt.
rapid, you know, uplift and erosion and transport.
Yeah, I mean, it fits, you know, it fits these predictions, these emplacement depth predictions fit pretty well. Like, yeah, I remember seeing the final outputs and going, pumped the erosion and pumped up. There's way too much. This can't be right. But and even with these thermal models, you know, they've maybe slightly over predicted if you're being really harsh on them, but generally they look pretty good. So it seems like things are in order, even though they do look really extreme. And I mean, that's what New Guinea is partially known for, you know, a place of extremes. Yep.
You said you've only looked at the you know, uplift vertically, not necessarily horizontally. Have you considered you know, modeling structurally using a sandbox? So in a more of a plasticine or sandbox setting, you can sort of give your guideline in 3D, especially how things might look like too.
Yeah, so that would be something like Underworld, which I mentioned before, which can handle those kind of deformation things. So it is possible. You need constraints which don't really exist widely enough for Papua New Guinea. We can already see the sparseness of some of the sediment isopacks. Yeah, so it's possible. The calibration would be extremely tricky though, to get that and the erosion together, but it's definitely doable. And like we have the computational tools to do it.
But just keep in mind the underworld models, they're great because they capture all of these things, fault mechanics, everything, you know, the thermal evolution. But they'll probably take months on a supercomputer and hundreds of processes for one model. And to explore the parameter spaces that he showed, you need 2,500 models like that. So I think the feasibility, I'm hopeful, you know, it'll improve in the coming years.
I suppose, yeah, you have to make some sacrifices elsewhere to include that stuff, to include the deformation stuff. Yeah.
Thank you.
Thank you for your nice presentation. How many features you have extracted from plate tectonic things and also dynamic topography, and also which features was the most important for your discovery?
Okay, so with the features for the mineralization predictions, that is like not my work. I'm building on that. That's Hassan's work. He had maybe from memory in some of those presentations, he had maybe 15 or so features, but 5 of them were, contributed to like 60-70% of the importance or the weighting that the machine learning algorithm assigned. And those were from memory, the nature of the seafloor slab, so the rate in which that slab was made at the ridge. So that's stored, and then by the time they subduct it, they found a huge importance for that. And the other stuff I can't quite remember, sorry. Now, the features that were most important for the landscape evolution side were the pretty obvious ones. So they were erodibility and uplift. So obviously, if you have a higher erodibility, you very easily move material down slope. So that had a high amplitude of effect. But what I actually found, which was quite important, was you can really control the morphology quite well using different fluvial models. So I tested a bunch of different fluvial models. So so you have a typical stream power law, then you can have transport limited versions of that. And then within the transport limited models, there's a whole different bunch of numerical implementations or models as to how you capture how the sediment that you are carrying in the stream inhibits or helps the ability for the water to incise the river bed. So those are really important for getting the morphology right, especially when you've got large scale, you're modeling a whole range. So morphology is quite important, and to reconcile some of the slopes, like the really steep slopes and stuff, you really need to tinker with the exponents and the different models and the erodibility of different sediments and things like that. So I think a big thing there was, the erosional model, because most landscape evolution studies just use stock standard stream power law, and they don't really test any other parameters and really think about it. They're looking at other things. So it's quite interesting to see how influential those things can be. And if you have the tools to calibrate them, it'd be very helpful to help you achieve a more realistic model.
I had a question around the volume. So you mentioned the offshore volume of sediment that you used to constrain the erosion. How well did that match up? And
well, I actually still underestimated the volume. So we got about 80% or 75% of the volume from the ISOPAC. So the ISOPACs, I can't remember what the volume was, but the models are really only achieved 70-80%.
So if here that you're over predicting erosion, but you're underestimating the volume offshore, how do you account for that?
So could be to do with the compaction laws that we're using. Also, the ISOPACs are interpretations of seismic data, so they're interpretations themselves. And
you're lacking some of the carbonates.
lacking the carbonates.
I mean, some of them get dissolved, right? But some of them do get.
And then maybe there's
the volcanics, right?
The volcanics, we're missing some volcanic component, and there's even maybe some sediments been driven off Queensland or something like that as well, which I didn't account for. So there's a couple explanations, and but it is interesting that there's a conflicting story that potentially over predicted erosion and under predicted deposition. So you kind of just
you'll be able to add the carbonate stuff in because there's a carbonates module. But the volcanic edition is just notoriously difficult because you need to constrain the time of volumes of the magma addition. And some have been eroded. And that's just notoriously difficult in these numerical models.
But I did do a little feasibility check to see the standard amounts of volumes that they predict from volcanism, and it could account for a good another 10% or so of that missing 70%, so we can get up to about or 75%, so we get up to 85%. But obviously, that's such a huge range of how much volcanic output, so it's hard to really say.
I think we have one final question online, and we might end it there. There was a question about, great to hear that you work with Oil Search and Santos. What data did they specifically assist you with?
So that was the sediment isopacks.
Yeah,
Yeah.
okay, yeah, perfect. Thank you. Nick says thanks for the talk, very interesting. Yeah, so I'd like to thank you, Addison, that was excellent.